Okay, hey there. I have a fun programming task today. I'm going to do some procedural animation. For context, at TinyBird, we're working on a new marketing website, and in addition to the practical textual information, we want some nice visuals, some decorations. So our designer sent over this as inspiration. Nice animation here, kind of vector field, representing maybe a fluid flow underneath. Now, we could implement this kind of a vector field by putting a rectangle at every point on a grid and setting the rectangle's angle and opacity based on some property of this fluid underneath, or maybe we could even simply do it as a two-dimensional noise. But I thought, since at TinyBird we're bird enthusiasts, we could simulate a flock of birds and use that as the basis for this visualization. So the birds can be flying around invisibly in the background, and these rectangles can indicate something about what the birds are doing. For example, in a given cell at a given point in this grid, we can set the angle of the rectangle based on the average heading of all the birds passing through that cell, and we could set the opacity of the rectangle based on the number of birds currently in that cell. So that's the idea. We can divide this up into two parts, basically. Part one being simulate some birds, and part two being lay this abstract visual over the top of what the birds are doing, and actually hide the birds so they end up being invisible. You can just end up seeing the effect of the birds. So I've done some initial work, and don't worry, it's relatively boring parts. Set up an HTML page, set up an SVG element. Now we could also do this with a canvas, but I thought, since it's so geometric, to me it feels a little more natural to do this with SVG. But there's advantages to both. Maybe this whole thing would be better on canvas, but I'd like to try it with SVG. So that's the HTML page, and then we have some JavaScript. We have a basic vector utility class for working with 2D vectors, which are going to come in handy for getting the birds to move the way we want them. We have vector addition, subtraction, multiplication, setting magnitude, getting the heading, that is to say the amount of rotation, which direction the vector is pointing. And then as I implemented those utility class methods, I went and added some basic tests just to check that things were working as expected. So that's the utility class for 2D vectors. Really going from scratch here. There's not much, I claim there's going to be not much needed to make something nice here. Then we have a utility function for working with raw SVG, which I like to do to avoid having to write this create element namespace all over the place. And then a class for a bird. So there's not much. This is what I envision being necessary to pull this off. We may end up finding we need more, but we basically have a position and a velocity value, each being a 2D vector, and then a way to draw the bird. So we have an SVG group element, and we're going to move the group around. And then what does the bird look like? It's a polygon, which we'll set as a child of the group, and the polygon has these points to draw this shape here, chevron. And then we have a bird instance. And then to make the bird move on a given animation iteration, we have this method called update. So we're going to take the position and we're going to increment it. And as velocity is a change in position, we can do vector addition, and we add the velocity vector to the current position, and then we get the new position. So the position has changed by what amount? By the velocity for that given interval. And then once we have updated the position, we're going to redraw we're going to set the attribute of the group element, transform attribute. We're going to set a translate for X and Y, and then we need to rotate the chevron, which we do thanks to the heading that we get from the velocity vector. So which way is the bird moving? That is, which way will the bird be pointing? And then we convert that to degrees, which is what SVG speaks. Now we have this function I'm calling main, where we get the SVG element. We set this global variable so that our class instances can work with it. And then we construct a bird. And when we construct a bird, we set an initial position, set an initial velocity. So this should be 100 pixels to the right in X, 100 pixels down in Y, with a velocity of 1 unit to the right and 1 unit down. And then, of course, to get that initial position and value to take, we need to call update at least once. So that's the setup. And so let's take it from here. What should we do first? I guess let's set up an animation loop. So to animate, we're going to use this request animation frame, and that takes a step function or an update function. We could call it step, and that's going to start us off. Now we need to define step. Step we could define so that it takes I think like elapsed, but let's try to get away without that for now. That would help to maintain the temporal properties, that keep the motion consistent across different frame rates, if our frame rate fluctuates, or if we're doing this on different systems. Before this kind of thing would go to production, we should address that detail, but maybe we can save it for later. To do properly handle, what do we call this? Interval, elapsed, time, delta. But we'll skip that for now, see how far we can get without it. So step, we're going to do the work. And then as the final task, we'll call it request animation frame again, and so on. And that's going to set us up with a loop. So what is the work that we want to do? We want to update bird.update. So every frame we want to update the bird. We can get rid of this. Okay, let's try running this. Nice. Okay, so our bird is progressing down and to the right at a velocity of 1,1, so 1 pixel per frame. And then it disappears out of bounds. So we could add a few more birds. Yeah, let's add another bird here. Well, here we go. Copy this block, and we'll call it bird2. And now bird2. Let's give it a different initial position. And same velocity. Let's go 1 to the right and 1 up. Okay, let's try that. Bird2. I think I see it here in the corner. Of course, we need to update bird2.update. That being updated. Okay, here we go. Cool. Okay, bird1 going down to the right, bird2 going up and to the right. So I guess I'll update this comment. What are we doing here? We're saying update all the birds. Okay, so in the animation step, we go through all the birds and we update them all. Now let's handle the birds going out of bounds. We could be fancy and we could try an approach where the birds have some motivation to come back to the origin somehow, back to the center of the SVG area. When we get to the flocking part, we're going to want the birds to be motivated to group together, but not to collide with each other, hopefully. So we want to maintain some affinity, but also some separation. We could also add in a factor of behavior where the birds want to circle and come back. But let's see if we can get away with something much simpler. And that's this classic teleport behavior, where you go off the screen on one edge and you appear instantly on the opposite edge. So bird, if it crosses the bottom, that is, if this, so we're in the bird class again, if this dot position dot y, so if we go down past the bottom, is greater than SVG height, then we teleport back to the top, teleport back to 0. This dot position dot y equals 0. Okay. Now the inverse of that, if this dot position dot y is less than 0, so if we're above the top edge, this dot position dot y equals SVG height. Okay, let's try that. Nice. Okay, so this bird 2 has successfully teleported. Let's see if bird 1 will. Okay, cool. Okay, now we should do the exact same thing, but for x, okay, and now instead of height, we're working with width. So if x is greater than the width, teleport back to 0. If x is less than 0, teleport to the right edge, to the width. Okay, here we go. So now we should have two birds that are always present and always entertaining us. Let's watch for running off the right edge. Cool. Cool, okay. Things are starting to come together. So, I guess we're not going to get very far if we hard code these birds. So let's get an array going. Birds is an empty list. Okay, now let's populate the list. So let's see, num birds. Let's start with 20. Let's do a loop. Yep. Here we go. Okay. Now 20 times we're going to construct a bird and push it onto the list. Okay. So bird new bird, set an initial position, set an initial velocity, add it to the list, and then we're going to update all the birds. Okay, we can do that. Birds.forEach bird.update. Okay, so for each bird, we call update. Now, if we run this, they're going to all be on top of each other. So let's do math.random. Give it a random velocity. Random's going to return a random floating point number between 0 and 1, I believe. Okay, so now we should have 20. Nice. Okay, 20 random velocities between 0, 1 and 0, 1. So they're all going down and to the right. Ah, cool. And they're starting to teleport. Okay, so we got birds going. We could say that this is good enough and skip right to the rectangles. But there's no flocking. We would like some flocking. Actually, let's do initial x. Okay. Initial y. And now let's do minus 0.5 so that, yes, okay. So now we're random velocities going between negative 0.5 and positive 0.5. Let's start the initial position in the middle. SVG width divided by 2, SVG height divided by 2. Okay, now they're starting in the middle. They're radiating outwards. Random velocities. We could speed that up if we wanted to. So now the top velocity is going to be 1. Yeah, I think that's nice. Okay, so we're making progress. And now let's get the birds to relate to each other. So there's this Boyd algorithm. I've always wanted to try to implement Boyds, but have not yet. And maybe we'll end up implementing it here, or maybe we'll implement a crude approximation. But if we read about Boyds, looks like on this article there's not an implementation provided, but we have these 3 rules. So separation, steer to avoid crowding local flock mates. So we might want to only pay attention to ones within a certain distance for each bird. Alignment, steer towards the average heading. So birds like to fly in the same direction. Alignment. All right, and the other 3 images. And cohesion. So birds don't want to drift apart. They want to stay grouped. They want to stay in a flock. Now I've thought about this a little bit in advance, and this word steer makes you think we want to define the birds based on a heading and a speed. And maybe we could perturb the heading, increment it by a few degrees or decrement it by a few degrees to steer, so that birds will come around, they'll veer towards each other. But after thinking about this, maybe we can achieve the same thing without actually implementing this kind of a set heading, set speed approach. We might be able to get away with this classic, as if they were points. You have a position in XY and you have a velocity in XY. And the bird just happens to be pointed where its velocity is going. So that's what I want to try here. And thinking through this a little bit in advance, I'm hypothesizing we can attain alignment, for example, by doing some sort of averaging of the velocities. So birds want to fly at the same way as their neighbors. So we can asymptotically move a given bird's velocity to be more like the velocity of the others. We can take stock of the velocities of the others, average them together, and then average our own bird's velocity with that. So maybe that gets us alignment. And then cohesion, we can calculate maybe the center of position, the average position of neighbors, and go towards that value. No, but I've already thought of this actually in advance. That would be, we could achieve that by simply going through all the neighbors and, as if it was like gravity, increment our own bird's velocity by the direction vector towards each neighbor. So we're gonna, look at the green bird here. The green bird's velocity is what it is, going north in this case. We want to add a little component to it, which is northwest, some components which are west, and some components which are southwest. And then as a result, I claim we're going to get this, tendency to move towards the neighbors. And separation, I don't quite have a clear way to do that with just x and y vectors. Maybe something will occur as we go through this, or maybe we can get away without it. Now, I'm not looking to implement the finest Boyd's algorithm here, just something that's visually entertaining. And I don't personally care too much if birds collide in 2 dimensions, because we can just use our imagination as maybe one went over the other and the other went underneath. So the plan is to try to get alignment and cohesion just with position and velocity vectors. So where to start? Let's try starting with alignment. So we're going to need to take a big step. And that is to get the birds to relate to each other. So maybe there's fancy ways of doing this, but the naive way, the brute force way, is just to do a double loop. So we're going to go through all the birds, and for each bird, we're going to loop through all the other birds. This animation is distracting me now. Here, let's go to a different tab. Okay, so for each bird, we're going to go through all the other birds. Now we're going to say others. Well, okay, iterate through birds again. Birds.for each. Others, other bird, right? Whoops. Okay. So update all the birds with respect to all the other birds. So for each bird, we're going to go through each of the other birds. So we're going to end up with this kind of O of n squared approach, this double iteration. But I think that'll be good enough. We just won't use too many birds. And I think it'll give something nice to look at that's adequately performant. Now for each other bird, so we're going to say if bird equals other bird, we'll do an early return, right? Because we don't want to compare bird to itself. Let's log this out. So we just verify that it worked. Bird is itself. Okay. Here we go. Malformed arrow function parameter list. Really? Oh yeah. Okay, we're getting lots of birds are themselves, so our class equality is working. Okay, so bird for each other bird. Okay, so we're getting to the fun part here. Here we go. Bird. So we want to... Okay, this is distracting me again. We want to say, bird dot velocity. So let's label this. What are we working on? We're working on alignment, right? Our velocity we want it to tend towards the other bird's velocity. So if we simply start adding other bird dot velocity. Okay, now we're going to have the vector sum of two velocities. And the vector sum, make a little drawing here. So if our velocity is like so, and other bird's velocity is like so, we're going to end up with a result velocity like so, and it's going to be longer, so we're going to want to then shrink it. But it is going to be closer. Every time we do that, our velocity gets closer to the other bird's velocities, and we're going to do that over all the other ones. So I think we might have it if we just do add and then we shrink it again. So multiply. Oh no, we have this function set magnitude, I believe. Set magnitude, right, gets the length. So now we're going to lose a little bit of the variance of the velocity, right? If we're always setting, we have like a fixed magnitude, bird speed equals 1. Might be richer if birds could have different speeds, but maybe this will be just fine to have the magnitude. So, all birds always fly at a constant speed. Maybe we're going to lose out on some richness of bird being able to catch up to other bird. But I think this will get us alignment. Okay, I don't know what else we might be missing. Let's just try running this and see what happens. Anything happening? Whoa. Have they all aligned instantly? It looks like in one single animation iteration they align instantly, so we're missing something. I'm going to pause the recording and think about this for a moment. Stand by. Okay, I have an idea. So here's our velocity, here's the other bird's velocity. Our sum is going to be like so. What if we scale down the other bird's velocity so that its influence is less? That's the idea. So other bird dot velocity. Now this is gonna... we can't just do set magnitude here, because that's going to mutate the other bird's velocity, and that'll mess things up. So we need to, we need to create a new vector 2D, and then we're going to end up possibly with a lot of garbage, but maybe that's not going to be a problem. Maybe there's a better way we could do this. Other bird velocity. Maybe we can come back and clean this up later. Also, we could implement a utility, a constructor to take another vector. Okay, so let's call this influence. That's going to be a new vector. So influence. Let's do influence dot set magnitude 0.1. Okay. Now let's try this. So what are we going to get? Oh, look. They don't overlap perfectly now, but they are super clustered. Oh, right, because they all start off at the center. Right? They all have the same initial position. Okay, let's comment this out for a moment and go back and make sure we're going to start them all off at random positions. So SVG width. So we're going to do math.random so we want the initial X position and initial Y. Actually, this is going to be let's call these DX and DY, right? Because those are the velocities. Now initial X, that's the initial X position, math.random, so that's a value between 0 and 1 times SVG width. Okay. So an initial X position, initial Y position. Okay, let's try that. Now the birds should start off. Cool. So they're starting off all distributed. Now let's go put this alignment back in and see how quickly the birds get aligned. Ha, okay, too quickly. But they're aligned. Okay, let's try this magnitude thing. They're super diminishing. Oh, look at that. Okay, okay. So we can scale it. Okay, here we go. Here we go. Steering, steering. Nice. Okay, so the scaling seems to be viable. Now we have all the birds flying in perfect formation. Have we achieved alignment? I think we have. Maybe we could introduce some randomness. So let's watch it again now at 1/10 of the potency. Okay, they're not getting aligned very quickly. Maybe this is too slow. Let's see. Yeah, that's quicker. Okay, so maybe we leave it here for now. So we got the alignment. And now let's try cohesion. Cohesion. So my vague idea is, as I mentioned, start computing the directions and in increment, start summing up velocities. Start shifting our bird's velocity in the direction of other birds. Let me think this through for a little bit. One moment. Okay, we're back. So the distance, the direction, we want to get the direction. This is the idea. Get the direction to the other bird. Actually, I wanted to leave a note up here. To do maybe don't make the garbage collector work so hard. Don't know if that's going to be an issue. but let's ignore it for now. So cohesion, so direction to the other bird. So we're a bird, we're going and looking at all the other birds that are not us. We're gonna try to get aligned. And if we're far away, we're gonna try to get closer. So we want a vector which is, what do we call it? I guess it's the direction. Direction to other bird. And that's gonna be the vector difference. So we're gonna be our position, bird dot position dot subtract. Is that not a method that we defined? Yes. So we take us, we take another vector, and we perform subtraction. Let's try it. Direction. Other bird. Okay. So I claim that's going to give us a direction vector pointing towards the other bird. Now, again, we got to be careful of mutating here, the way that this utility class is defined. So this is going to mutate our position. And I don't know if we want to do that. I think we want to mutate our velocity. I think it's more elegant, more accurate to say, right, let's go back and look at the update function for a bird class. Right, that's what we're doing. We are a bird, we are going, we set our speed, we flap harder. And thus our position changes. That's kind of the way of nature, so we don't want to be mutating our position, we want to be mutating our velocity. I think this is the physicsy animation engine way to do it. So instead of bird.position, we're gonna, well, we want to get the direction. Okay. And the direction's got to be a new vector. Okay, I think I want to go to the utility class and implement a constructor. No, let's not get too distracted. Const direction equals new vector 2D bird, us, bird, bird dot position dot x, bird dot position dot y. Okay, so here's our new vector. Again, maybe garbage collector. Probably worth coming to think about that at some point. Now we mutate our direction vector by saying direction dot subtract. So direction starts off as our bird's position. We're going to subtract, let's draw this out here. So if our bird's position is you know, here, and other bird position is like here, okay, we want to, what do we want to do? Us is here, other bird is there, we want to get this vector here, and that's going to be this one, our position, minus the other bird. That's what I claim. Our position, right, which is here, minus the other birds. Okay, so that's a direction. Now we want to be like, okay, us, bird, we the bird, we want to modify our velocity sum by this influence. And actually, let's scale it. We can call it direction. Direction. Let's set magnitude. So same type of thing as above. Let's start off 0.1. What the heck? Okay. Now, I guess if I got this subtraction backwards, it's going to be the opposite of cohesion. It's going to be repulsion. Maybe. Let's see. Ugh. Okay. Where did the birds go? Okay, bird.velocity.sum is not a function. I think because we named it add. Okay, whoa! These birds are... Huh. Okay. Okay. They were jittering, and then it exploded. We got some nads coming in. Fascinating. I don't know. Let's try to diminish this. Yeah, something funny is happening at the edges, huh? These birds, they're getting glued or magnetized to the edges. What the heck? Let's try diminishing this one more. What are we doing? Are we cohesing? Are we cohering? The birds are still getting drawn to the edges. They're getting aligned. They're all going north. Okay, maybe voids is not as simple as I was thinking. Maybe we will have to go look at a reference implementation. But not quite yet. Let's see what else we can come up with here. Oh, look, these two broke free. They broke free of the magnetism of the edges. Fascinating. One thing we haven't tried is inverting the subtraction. Let's try this. Direction other. So the direction starts as the other bird's position, and we're going to subtract our position from it. Are they going to cohere? Are they going to cohere? Are they grouping together? Kind of. Maybe that was it. Maybe I simply got my directionality, my vector subtraction backwards. That's the problem with subtraction. It's not, what do you call that, commutative? Doesn't work backwards. Look at this. These are like migrating geese. And they're turning. What caused them to turn? North? Northeast? Okay, what's going to happen here with this? This crossover. When they kind of oscillate back and forth, are we going to end up in a single conga line? Okay, maybe we have something here. I'm not seeing it glitchy. This is a nice way to check that our vector subtraction is correct. There's this saying in computer graphics that if it looks correct, it probably is correct. That kind of feels like a cop-out, but I mean, our goal is to create something that looks nice, and when we subtract the vectors in this way, I think it looks nice. So maybe we have alignment and cohesion, and maybe all we need is separation. Somehow I thought we could get away without separation. So, alignment, cohesion. Let's run this one more time. Yeah, the birds. They start off, they notice each other, they influence each other. How the heck are we going to implement separation? I mean, I suppose this is the end state of a system with only alignment and cohesion. A conga line. Right? Because we don't have the ability of having differential speeds. So there's no way for birds in the back to catch up. That might be fun to go back and implement at some point. I guess we can do some sort of a distance. Yeah, okay, I thought of this in advance. Distance to other bird. And we can say, if distance is, threshold, if we're beyond a certain distance, or if we're within a certain distance, oh, that's cool. Right, we're going to get this crossover again. Here we go. We got two conga lines. They're going to cross over, and the birds will try to cohere. Oh, pretty good. Kind of a little oscillation, and then one single conga line. Now, is there any way that they're going to break free of this? Maybe not. Oh, there's some perturbation. Ooh. When they go past a boundary, it like zips, it like unzips. Okay, here we go. Cool, they're going to oscillate. They're going to converge into one single conga line. Okay, now we're going to have to wait a while. But did you catch that? Let me see if I can recreate that. So we get to a conga line, and if it crosses the boundary, and then we do the teleportation, somehow half of the birds end up, the conga line gets divided. So I guess this is one of the bugs that I was foreseeing vaguely when we implemented this sort of naive teleporting. Okay, they're getting a single conga line. Its directionality has a substantial south component. Okay, let's watch what happens when it goes down past the south boundary. Do we end up with two? I don't know what happened there. Maybe teleporting is not ultimately the way. Maybe the way is some sort of a fourth rule that tells the birds to get back to center. Let's watch this one more time. Going up past the bottom, do we end up with two conga lines? Kind of. Maybe it has to do with the shallowness, the glancing angle. Okay, I could get entertained watching this and contemplating for hours. But let's see if we can implement some sort of a, what was the term that they used? Dispersion? Separation. Okay. Okay. I'm remembering back to me premeditating on this. So this distance idea, maybe we can apply it to the cohesion, and maybe we can say, hey, bird, only cohere if your other bird is close to you. In other words, don't pay attention to faraway birds. So we do a threshold, distance threshold thing here. Distance threshold, only cohere if neighbors, if other bird is sufficiently close, right? And maybe we can leverage this teleporting behavior to our advantage. Once it teleports, it gets far away, and then we stop cohering with it, and maybe it starts to take on a life of its own. Let's see. So threshold, okay. We're going to calculate a distance. Do we already have that? I guess it's the length, the magnitude of the direction vector. So let's say const distance equals direction dot magnitude. Okay, right? That's the method we defined, I believe. Yep, the square root of the sum of the squares, classic. Pythagoras, thank you. Distance, let's log some of these out. Just to see a sanity check, it should be within the width and the height. Yeah, we got some distances here. I guess the biggest distance is like the diagonal. Okay, those look reasonable. Now, we got a distance. What are we going to do? We're going to do a threshold. If distance is less than, let's say, 200 pixels, right, our SVG is 600 tall and 800 wide, so if distance is less than 200, then we cohere. Okay, why not? Let's try it. Huh. How come the formatting isn't working? Okay, anyways. Refresh. Okay, cohering only with neighbors. Hopefully we should get like different subflocks. Whoa. They all cohered instantly. Wait, they're not cohering? Oh, maybe they can't because we don't have differential velocity? Maybe this is too strict. Let's try 400. Oh, maybe some regime change happens if the distance is like greater than half the size of the canvas. Okay, somehow... What do we got here? They're aligned. We got alignment, but the cohesion is weak. Yeah, we're not considering... Oh, but maybe we could boost it this way. So we got two things to play with. We got the threshold. Ooh. Ooh. Okay, what's happening? What's happening? This is fun. Okay, they're flocking, and they're radically... Oh, they're so focused on being close to each other. It's adorable. Let me zoom in here so it comes through better. Whoa, what just happened? They got out of it. They snapped out of it. So is this a way we can have like cheap flocking with only two? That's not going to be so fun to see on the visuals. Although maybe it will be with the rectangles flipping and flopping. There'll just be like a cluster going through. Okay, that's not so fun. Okay, so we got to tweak. We got to refine. Let's go back to 200 pixel cohesion threshold. Are they cohering? Yeah, I see an influence, with neighbors. We're seeing some fun looping back around, although maybe that's too much. Maybe it's not very bird-like. I don't know about the tight turning radius of birds. Maybe this reveals the weakness of our implementation in not working with steering, where we could have a steering limit, a steering speed limit, essentially. Maybe what we're implementing is something more like mosquitoes or flies. This is fun to watch. I guess I don't like this global alignment. Let's try... Whoa, what causes them to spontaneously shift? Maybe it's the teleporting. But it is kind of a weird side effect. Maybe a convenient one. It's like the birds have a personality. It'd be fun to implement wind too and have them deal with different wind. I guess wind is a fluid, so this could be like a wind field and the birds... Okay, we could take this to so many places. Yeah, let's do distance threshold on the alignment too. So we're only going to align if distance is sufficiently close. Right? So add a note here, careful. Mutation. So we're going to use the distance. We're going to use the direction. Distance. We're not going to mutate the distance. So influence, right? What is influence again? It's for the alignment. So we'll say if distance is less than 200, do all this, right? Okay, now alignment, we expect it to only happen locally. And hopefully we should get subclusters. So, you know, like among the total population of birds, we get some going one way, some going another way. Oh, I don't know if I like that. Just end up in this maniacal vortex. Oh, this is wild. Why did that happen? If distance... So don't get aligned unless you're sufficiently close. Don't cohere unless you're sufficiently close. How are we going to get a breakup? Maybe let's not... Oh, and now they just exploded again. What? Okay, maybe we're fine here. Maybe this is a sufficiently entertaining flocking algorithm. It's got some personality. It's got some trouble. These birds, you might think they're defective, but maybe they are. Look at that. They get fed up with each other, and then they part ways. And then... Okay, we got like subflocks. Look, these are the subflocks I sought. I sought subflocks, and here they are. They pivot. They spin. Okay, these are just spinny birds. I guess... Okay, here we go, here we go. They're together, they're together. They crossed over. Some got teleported, some did not. And then they say bye-bye. Okay, I think this is sufficient to make a nice visual for a marketing website. Maybe the biologists are not going to learn much from these virtual birds. But let's make them a little bigger. I don't know. I like it. I think... I think we could keep tweaking it. But this already might look nice with the vector field superimposed on top. Any last things we could try? Yeah, let's try increasing the number of birds. So we started off with 20. Let's try 50. Here we go. Okay, okay. It is kind of a bummer that they all do have the possibility to concentrate in one crazy nucleus. Oh, look, we got a conga line going again. Uh-oh. That's uninteresting. Maybe we're not going to get away with this. Oh, and suddenly they dispersed again. We have like a shock wave traveling now. Wow. But the teleporting does give us some nice randomization. Here we go. We got two groups headed towards each other. I'm not such a fan of the crazy pivoting. I guess we gotta implement repulsion, separation. I don't know if this is gonna be sufficient. Okay, let's take a break here for a moment. Okay. So after taking a look at it for a bit, I've noticed that this threshold is backwards. The cohesion we want to happen at a distance. When the birds are far apart, they want to become aware that they have flown far from the others and they want to then come back. So what I had this whole time was if distance is less than 400, but things change when we do distance greater than. Let's check it out. Now, okay, maybe not that alone by itself. Oh boy. Or maybe I just needed to get rid of that second condition. Let's see. If distance is greater than, then we cohere. If distance is less than, then we align. So we want to align if we're close. We want to cohere if we're far. I think this is gonna take us in a good direction. So let's try diminishing the potency of the coherence. See? Look. Okay, this is something that's more pleasing. We don't have this crazy jumbling anymore. It would be nice if there was better alignment. This is just kind of a chaotic swirl. This idea of flocking of the birds going in the same direction together isn't quite on display here, but maybe we can tweak the relative potencies so the alignment is stronger now. Okay, seems they're all converging still on the center. So maybe we only want to cohere if the distance is really big. Let's try if the distance is 600, then we kind of turn back. Let's see. So all these ones they kind of homed in on the center. But what causes this turnaround? Thinking maybe the distance calculation is flawed here. Anyways, this is an improvement. It's hard to say whether to keep playing, to keep going down this road of the pure vector approach, or to say enough's enough, and another time come back and implement a proper steering approach. This may have been a misguided adventure into this naive idea of how to get flocking going. In any case, thanks for joining me on this little coding adventure. See you next time.